Hello and welcome to this video tutorial for Adapt Builder 2018.1. In this video tutorial we're going to be talking about evaluation of manual design cuts as compared to design sections that are created automatically along design strips, and we're going to look at a few of the new features available in Builder 2018.1. We're going to start by importing a Revit file into Adapt Builder using our IMP Exchange format. There will be a few adjustments required to overlapping elements which stem from the Revit file, so we'll show how to make those changes and do some simple modifications to the model inside of Builder. And then we're going to model a few things in Builder. We're going to model loads, and we're also going to model tendons. So in a portion of the model we might have interest in determining stresses, moment capacity, reinforcement, deflections, and so on at particular locations in that slab. And the program doesn't require the user to generate section cuts at every location in order to make that evaluation. We can go ahead and isolate and make our own custom manual design cuts and then evaluate those cuts using some of the new graphical tools in this version. So we're going to go ahead now and get started. And what we're going to do is we're going to import a Revit file. We're going to look at one specific level and one area of a level, add some post-tensioning to that level, and check a few locations where we might have interest in looking at stresses, moment capacity, and also demand for the few design cuts that we'll make. So we'll start out in Revit. We're going to have this file. We have this Revit file. We're going to take one of these upper levels. We're going to say, for example, level 10, a typical floor. And we'll go ahead and just under Analyze, we're going to export this to Adapt. So we'll select the option to export the data. And we'll call this level 10. I'll go ahead and minimize that. I'm going to open Floor Pro. I'm only going to be working in single level mode, so I technically don't need to have Edge turned on unless I wanted to analyze the multi-level structure. We're going to just be using Floor Pro with PTRC design scope, and we'll use US unit system here. We'll select OK to open the interface, and I'll select File, Import, IMP. We're going to navigate to the location where the file was saved, which is here in the onboarding folder. I'll select that file, and I'm going to create a new model for level 10. So we're going to select level 10 only. You can see it's going to be imported to the current plane. That's the active plane by default when we open and create a new model in Builder. There are no loads or combinations, so we'll go ahead and add those in the model. This tells us that there's a column that already exists at a specific location, so we'll find that and fix that. We now have this level. If I go to a 3D view, this is the file that we have, and I know if I try to mesh the structure, immediately the program will flag that error regarding the stacking columns, and it will highlight the location, so we know that this is the location here. I'll delete one of those. If I delete it again, you'll see it deletes the original column, so I'll just undo to bring that back and have that as part of the evaluation. We're going to mainly focus on a couple of areas up here that might be of interest. Just as an example, you can see we're actually missing a column or two, so we're going to add these two columns. I'll just Control C, Control V, and I'll just go ahead and add those over to here. Again, it gave us the warning due to the copy, so I think this one also needs to be deleted as well. So every time you do a copy, it will flag columns that are duplicates, and that's what happened there. So we're now going to just mesh the structure, make sure that we can mesh this and analyze it under self-weight before we start in on generating our design cuts. So I'll save the file. Okay, we'll go back to the mesh operation and we'll mesh this with the default settings. And now we're going to execute under service total. So these are just default combinations that are associated with the design code, which is ACI 318.11. In this case, we'll select the service total condition and run through the analysis one time just to make sure that this is working properly. So if we look at the new results viewer here, we'll select the service total combo under analysis. I'll go to the deformations, Z direction, and you can see we have a problem. So if I turn off the shell elements, we have a huge deflection over here, which makes it really difficult to determine whether or not there's connectivity established elsewhere, because those contours are all essentially the same or within a very small range. One thing I can do is I can change the range of the contours. So I'll go ahead and right click under the minimum value. I'm actually going to put -2 inches. Maximum, I'll leave this at 0.15. And now you can see the range shown here. So this tells me that, while there's a huge displacement here, there's still connectivity over in this region where we're going to focus our results on. And I can go back and even tighten that range up a bit further. Maybe we'll do 1 inch to 0.15. And again, we have the contours shown here. So if we were to go back and actually try to fix this area, we can see we're getting large displacements here because of this cantilever. I'll take these and just add those as columns there. There may have been columns missing also in that location. So when I make a modification to the geometry, I want to go back and remesh the structure, and then we'll go back and execute the analysis one more time. And then the program will auto reset the range to be the new maximum range, and you can see it's about 1.45 max deflection. So this looks okay now. We're going to clear the results there. And we're going to add some PT. We're going to, again, focus on this area. We're going to assume we have some post-tensioning. The banded direction we're going to say is along this line, and then the distributed direction might be along this line. So we're going to add a few post-tensioning cables here, and we're going to terminate one of the bands. Will terminate at this edge. The other band, we're just going to bring that down and anchor it here. The same thing, we'll anchor that there, and then we'll just add the distributed cables in this location. We're not going to be doing any design strips. We're going to focus solely on generation of manual design cuts, which is an alternative to full-fledged design strips if you're, again, wanting to focus in on a specific area and evaluate specific areas of a slab. So the first thing I'll do is add some loading. Let's go ahead and select the model, the slab here. I'll go to loading, patch load wizard. I'm just going to add some uniform loading, 20 PSF for dead load, and under live load, I'm actually going to add, let's say 80 PSF. Okay, and we're going to add some post-tensioning cables. Because I'm manually adding the PT cables, I need to just make some assumption as to what the cables are. This might be an as-built type of a condition, so we're just going to arbitrarily select and add cables to the model. We'll just go up here to tendon. I'm going to add a cable here. So we'll start it at this edge. I'll turn on snap to nearest and then run that up along this line. I'll terminate that at the edge of the slab. Okay, and then I'll double click on the cable. If I wanted to, by the way, if I wanted to change the color of the cable, I could go to visibility, and in visibility, maybe under tendons, I'll change this color and I'll make those tendons, let's say, we'll make them blue in this example. So there's one uniform or banded tendon. We're going to say that this tendon is 10 strands. These are 1/2-inch diameter cables. We have a specified effective force, and then we have our profile for the cable shown here. So we're gonna leave that as is. The next cable I'll add will start here. And then I'll add one more, and I'll start that cable. I need to zoom in a bit just to be able to snap properly. Add that here. In this case, I'm going to pull the tendons off of the column center, so I'll turn off my snap tools, and I might, snap away from that column center just to avoid having it encroach and extend maybe past the slab edge if that's a consideration. This cable we're going to terminate at the face of this opening, so I'll just say right there. And then we'll go in and modify the properties. We're going to say this is 20 strands for that interior bay. This is the tail on the bottom side of the modeled tendon in the graphical plan view. We'll say that's a cantilever down shape. And then here where we have that opening, or that's on the third tendon, we're going to use a cantilever down shape there also. So we'll come over to this one. We're going to use 10 strands here. This will be cantilever down. We have a short span. This third span is quite short, so we'll change that to a straight shape. You might have a little bit of uplift. We'll just change it to straight. And then this back span, we're going to say that is also a cantilever down, or maybe a straight shape to the edge of the opening. This is going to be 10 strands. Again, 20 strands and 10. Now we could always use the display manager to turn on the control points, and I'll also turn on number of strands as specified. So that gives us more control over the data that's used here. So let's go ahead and model the uniform cables. I'm going to come back and model these at the edge of that opening. We'll start right here, and we have one there and then another there. We're going to say this is 2 strands, and we'll set the profile like so. Now if I want to copy this in an array with, let's say, 3-foot spacing or whatever spacing it is, to copy and move this, we would either need to go to modify by coordinates, or we can do some graphical with a reference point and then copy multiple times. The best way to do this would really be to rotate the model, because it'll be easier to copy in the X direction or the Y direction orthogonally versus determining the X and Y movement for that tendon. So we're going to rotate the entire model. We'll make sure we have everything turned on. I'll select everything. We're going to go to rotate, and I'll go up and grab this corner. I believe the rotation here is going to be 6 degrees. Wrong direction. It should be -6. Let's do that again. So we're going to say -12 and move, and that rotates those components. You can see that the columns are askew, so we need to actually rotate the columns back. So to do this, I'll go to Home, select by type, column, and we're going to go to modify selection, and for column, the rotation angle we're going to say is 270. So our columns are back where they should be. Now we can easily copy this tendon down. I might want to realign the end to make sure it's right on perpendicular, something like that. And then I'll take this and I'll copy it down every 3 feet. So we'll say tendon, or excuse me, modify, copy by coordinates. This is in the negative Y direction, 3 feet, and we're going to make 30 copies. Okay, we may need to make just a few more copies here. Okay, and I'll just delete out those. Actually, let me just delete one of them. Oops. Okay, this one I'm going to move over to that face, and then I will right-click, insert another point, and then I can move that control point over to this location using snap intersection. This is now a 3-span cable, just made off of a copy of a 2-span cable. We'll save this, and then I'll copy that down. I'll end the tendons, let's say, in this zone at that corner. So we'll copy that. Again, -3 feet, and I'll make a copy of that let's do 6 copies. A few too many, just delete those out. And now we're ready to evaluate this slab. I will adjust this one vertically, so we'll copy that one up one time. This will be in the positive Y, so we'll use a 3-foot copy. I'll come back and adjust that shape on the end where we connect to the opening. We're now going to go ahead and turn off the display of the tendons. I'll use from the tendon ribbon, I'll use the show tendons option just to turn the tendons off and on. And we're going to go ahead and create some manual design cuts. Now, before we do this, we'll just do a quick refresher on generating automatic design cuts through use of strips. And this is what's most commonly done for a two-way slab where we want, an evaluation of cuts at every location along every frame line in 2 directions for a two-way slab. And that would require a user to go to floor design. We would create, for example, design strips, and I'm just going to go ahead and just create these end to end, but we would create a series of design strips like so. This is not the way I would advise. I would actually be clicking on each column, but just to illustrate the concept here. And then since I'm only evaluating this wing, I can essentially cut off the remainder of the slab using an X direction boundary or the splitter line. We would do the same in the other direction, in the Y direction. So after you create the design strips, we would generate the design cuts, and now we have cuts at increments along the length of the design strip. And so this is a way that we would generate cuts at every location in a slab. Now, if a user knows that they may want to evaluate just a specific region, it might be a new design where you can use some engineering judgment as to where you might get the greatest stress or greatest moment. It might be an exterior bay that has greater length than, let's say, interior bays. Any requirement for the need of isolated cuts for the evaluation of a new or an existing slab can be done using this new tool, create manual design sections. This is also under floor design, and we're going to go ahead and just create a few of these sections. So I'll go ahead and I'll create one in both directions at interior column. So you can see there's one here. I'll do the same at an exterior column, and this cut we actually might want to stretch out a little further. Okay, I may want to do a corner column, so I'll do a cut, let's say here, and I'm getting them as close as I can without fine-tuning the cuts to the column face. So you see we have a few cuts, and then I'll do a couple of locations, let's say in the span. So we'll do one here in this span, I'll do one in the mid span here, and I might also do another, let's say, out here. And we could also create a cut where we might want to evaluate just the deflection in a span. So I might actually do a cut, for example, here. We're going to use these cuts really just to evaluate maximum deflection over the integrated length of the cut. So we have several cuts that we've generated. I'm going to go ahead and under analysis, I'll mesh this slab again just to kind of refresh. We'll go back and mesh the slab. And we're going to now analyze the slab. And I have under loading combinations, I just have a few default combos. I have 2 strength, 2 service, and initial. The strength will mainly be used to evaluate moment capacity versus demand. Service would be used to evaluate, let's say, the stresses and also the deflections that we've for the cuts that we've set up for deflection. So we'll go back to analysis, and I'm going to run the analysis for those 5 combinations. And that's been completed. Now, if I don't want to see those shell elements, I can turn those off. There's a few ways I can turn them off. I could go to the analysis ribbon, which I'm already on. This is probably the quickest way. And under the visibility panel, we have the option to turn off shells or just turn off everything related to analysis. So all of the analysis elements, meaning nodes, frame elements, shells, everything can be turned off using this first button, or you can isolate individual element types. Here I would turn the shells off and on. You could also go to visibility, and under the view settings panel, the finite element tab, we could turn off shells also using this kind of a legacy option for display. We'll go back now, and I'm actually going to turn on the manual cuts. That's shown under FEM here, so we'll turn on the manual design cuts. Those are back on screen, and now I'm going to design these. So if I wanted to design only one or a handful of design cuts, I could select those, and then under floor design, use the option to design the design cuts. In this case, I'm just going to leave everything unselected, and I'll use the option to design the design cuts. You may see my icons have been shortened, or they've actually been reduced in size. That's just due to the resolution of my screen. So if you're not seeing the same on your end, that's okay. The program will auto fit all of the icons within the screen based on the resolution. So we'll go ahead and design these cuts. Okay, that's been completed. Now what's new to the program is the following. If we look at the new result display settings in this browser form, I can select my combinations under the loading tab. So just to boil this down to, let's say, a service combination and a strength combo, we're going to first select service total. And if I look at service total, I've selected that here. I'll go to analysis. Once you've created a solution or designed the manual design cuts, this new option will appear in the analysis tree as compared, for example, to regular design sections. This is for manual design sections. So we'll expand that. The first thing we'll look at is deformation. And we had 2 cuts located here and here, and we want to see what the distribution of deflection is within this panel over the cut length. So we'll go select that, and it will show it for all cuts, but these 2 are the ones that we want to generate to show mainly for deflection. And we can see that the program gives some span deflection ratio. This L is based on this cut, so the maximum deflection over this distribution divided by the cut length is what this number represents. We could also turn on the max min values. So in brackets, we'll see the maximum and the minimum values of deflection at any location along that cut. And you can see the minimum is 0.02 negative, that's downward. Maximum is 0.26 negative downward. And then for this cut, we have 0.23 out here in between these 2 columns, and then in the middle of this panel, the max deflection is 0.27. So this is a nice handy tool to evaluate deflections very quickly using design cuts. And that's the first option here under the manual design section tab. Let's go ahead and turn that off. If we go to actions, this might be more applicable to strength, so we can check things like bending, axial force, shear, any of these actions listed, we can produce a cut diagram for those actions. And for example, at this column face from this point over to this point, this cut length, and we could actually double click on the cut to get more properties associated with it. This will also show us, for example, mechanical properties, area, moment of inertia, Y top, Y bottom, design section. So this gives us the actual geometry of the cut. This cut's 216 inches. This is similar to what you would be seeing on a design strip if you went and evaluated a design section. So this will also re-import, or it will report the base rebar, any calculated rebar required for the section. So this is additional information that the user could tap into for this design cut. We're going to focus mainly on what's shown here in the graphical report. So the moment integrated over this line is negative 100.86, and this line here is negative 141.96. This is due to service. These are the max and min values along the cut line, shown in the brackets again. This again is more useful, I think, for strength design, where you want to see, well, what is the moment that the program is generating rebar for in terms of factored or ultimate demand at the column or at wherever the cut line exists. We can also check stresses. This is more in tune with what we might check for serviceability requirements of the PT two-way slab. So at these cut lines, I can turn on the top stress, and you can see again for this cut line here, the stress is 327.2 psi, and that's in tension. Positive is tension, negative is compression, and that's 86.2% of the allowable. The allowable stress is actually defined in the criteria under allowable stresses. You can see it's 6 square root of F prime C, and that value F prime C is dictated here as part of this material property. So we have an allowable of around 374. The actual stress is 327. The stress along this section cut is about 13 to 14% greater than allowable. So this just gives you a percentage of allowable shown with the actual stress value in PSI. PSI is the default. The user could change the stress value over under the settings. We can change the unit system here for stress. For example, if I wanted to report it in PSF, I could make that modification. If you wanted to change it to a different unit system altogether, you could change that here under result unit system. That's under the settings tab. Bottom stress, here negative value would indicate compression, and you can see we're well below the allowable for compression, which is 0.6 times F prime C for the concrete. Out here in the mid bay where we might actually have positive bending, we would have tension on the bottom, and that's what's shown for this cut, and so on. So you can see here we also have positive bending, about half utilization of the allowable. We can do the same for pre-compression. There's two options for pre-compression, FEM and number of tendons. The former is related to the axial force in the slab, which is subject to the axial restraint in the slab. The latter, the number of tendons, is related only to the number of tendons cutting through the cross section and the summation of their force associated with the tendon. So if we check this option here, number of tendons, we can see, for example, we'll go up here, we have a pre-compression of 137 negative. That's in compression, obviously the negative value, and we're at about 10% over the allowable. The allowable is actually set under, if we go under display, pre-compression minimum allowable is set to 125. So this is about 10% greater, which is okay. And the color indicates that that's also okay for this condition. Now, if you wanted to make a manual check, we could take this, show the tendons. In this cut, we have 4 tendons times 26.7. That's the effective force divided by the area of the cut, and you should get that value for precompression shown there. Now let's go ahead and go back to loads. I'm going to change this to a strength condition. You could also do an envelope of strength. We'll just do strength dead and live. And we're going to look at investigation. So for all of these cuts that are produced, we have capacities. The program will report the capacities. We'll go over here now. And we report the positive and the negative capacity. Positive obviously is the positive bending capacity, negative bending. And for the cuts, we just report those two values separated by the comma. You can also show the capacity with demand. So for example, this is telling us that the positive capacity is 31 kip feet, the negative is 135.3. The demand is actually 0 positive demand, which makes sense at the column face. The negative capacity is negative 60. And if we take a demand capacity ratio between these two numbers, you can see it's 0 for positive. There's no positive demand, but it's 0.44 for negative. And the program will flag locations where the demand does not meet or the capacity does not meet demand. They should all be green if we're actually designing the sections. If we go back and we were to do an investigation versus design, then we might see that in some locations we don't have enough capacity derived from the post-tensioning only because I've added no non-pre-stressed reinforcement in the model, and that would be done using this investigation tool. Okay, so that's the investigation option. We also have this option, contribution of pre-stressing to moment capacity of beams. So this is where we may want to limit the amount of rebar or the amount of post-tensioning and its contribution to the overall capacity might be 25%. That setting is actually defaulted to 25%, and it's located under analysis and design options and criteria. If we look down here at the bottom, check if fraction of bending strength of a beam provided by pre-stressing exceeds some percentage. Right now it's not selected, so if I check this, you can see nothing shows up because these aren't beams, these are two-way slab sections. And then finally, the design criteria just shows us what they're being designed as. Okay, so those are the different options. One additional option we want to show here is under the option for deformation, or excuse me, it's under the option for actions. We can check contour cut. And what contour cut does is if we go to the slab options up above, we have several different types of contours. We can look at deformation, we can look at moments, stresses, shears, anything that is associated with a contour result. We can produce a distribution for that result. So we're going to select contour cut, and let's assume we're looking at the Z deflection. So over these cuts, the program will show us the distribution of deflection, and this has already been shown under the deformation. So this right here basically produces the same thing, but you might actually want to see this, for example, if you wanted to look at the distribution of moment about the x-axis along these cut lines. This will produce that contour distribution for every cut line that you've defined with values. So this is something also that's new to this version. Okay, so what we're going to do now, just to close, is we're going to go back and we're going to select floor design again, and instead of design I'm going to investigate. And we touched on this a bit earlier about doing an investigation versus a design. The program will produce capacity, but that capacity may not actually meet the demand required for a particular section. And we can see again under manual design cuts, if we go to investigation, moment capacity with demand. Earlier these were all red, or excuse me, all green. Now we have a couple of locations where we don't have sufficient capacity for the section, and those are flagged as pink, shown here. If we zoom into one of those, we can see, for example, The capacity positive along this cut is 193, but the demand along the cut is 232. We have about 20% over the allowable, or over the capacity in that case, and then the same thing here, we're about 30% over. And this capacity that we're looking at is derived again from the concrete and the base reinforcement that's been entered into the model. In this case, the only base rebar is the post-tensioning. So we could add some localized bars in these locations to go back and check capacity if those bars are reflective of what you're checking for an existing condition. If you have any questions about this video or about the new version 2018.1, please contact support@adaptsoft.com. Thank you.